Hi, structural friends. This is our last video on influence lines, and now we're going to look at influence lines for complex structures. So while for determinate structures, all the influence lines remain linear, for complex structures, the influence lines will not be linear. But it's useful to do this just to kind of see what structural response would be. So in this case, I'm looking to draw the influence line for the axial force in member EF. And so basically, if we apply the equilibrium principle, we just want to move that one kip to different points along the length and calculate what the force in EF is. So I'm going to move it from point A to point D to point F to H to B, right? Now, when it's at point A, it's pretty easy to see that the force in EF would be 0. Now, when we're at point D, what is going to be the force in EF? Basically, I'm just going to run a truss analysis and then solve for this, right? So this might force us to have to run 5 truss analysis. And so, we learned some structural analysis software in this class, so don't be afraid to use that software to do this analysis. In this case, EF is a zero force member as long as the load is not applied at point F. And so when x equals 20 feet, we see that the force in member EF is going to be 0. When we move it to, when we move that one kip load over to point F, then we're actually going to have a value and we're going to actually have to solve for it. So that's what I'm about to do here. I'm going to erase it from point D, put it on at point F, and I want to then run my analysis. Again, this might be a difficult analysis. It might not be. In this case, it's easy because I can just look at joint F and I can do some forces in the Y at joint F to quickly solve that FEF would have to be one kip tension under this applied load of one kip at this point. And then from the same logic, whenever the load is not at point F, it's a zero force member. Now, just like before, because this is a determinate truss, the values of the influence lines will be linear. So even though we do have to move it to all the locations between the joints, we'll assume a linear behavior. Now, strictly speaking, in a truss, we can't apply loads between the joints. But imagine on your bridge deck, if you were halfway between points D and F, the way the bridge deck would be arranged, basically like half that kip would go to point D and half of the kip would go to point F. And so really the force in member EF would be like 0.5 kips under that moving one kip load. Hopefully that makes sense for the influence line for the internal force EF. I want to do the same thing for a floor system. Again, the calculations might be a little bit more difficult, or just, we have to keep track of our load distribution. So in this example that we see at the bottom of page 16-7, we have a one kip moving load across this floor system. Now, first we have to do a tributary load breakdown for the slab. And so when the one kip is between, points on the slab, you have to figure out like basically where I have the one kip load drawn in there. You could imagine it would be about 0.25 kips at point N and 0.75 kips at point M if that was like 3/4 of the way across. So that just gives you an idea of how you would figure that out. And then you would have to do the truss calculations to figure out what the values of the different points in the truss would be. So again, a little bit more complex. Again, linear, as long as it's determinate truss, the influence lines would be linear. Again, use structural analysis software to facilitate this. Now we're going to take a look at the influence line for a indeterminate structure. And as I mentioned at the start of this video, for indeterminate structures, the influence lines will not be linear. They will be nonlinear. So what we're going to work on here is just drawing a qualitative influence line just to understand how structure would behave. And like I said, with a moving like truckload, maybe you could then figure out some of the major points or maybe points you would want to check to maximize like the reaction at a particular point. And so that's what we're going to work on in this segment. We're going to look at first the influence line for one of the reactions. So maybe we look at the reaction at point B. And so we're going to sketch in the influence line for point B. So just as we did before, we're going to draw in the structure as it is. And so here I'm just drawing all my support reactions in. And then I'm going to remove the reaction at point B, and I'm going to shift it up 1. But now you have to imagine I'm just shifting this up 1, but now the whole thing is bending to accommodate this. So what is my displaced shape under that bending, right? If I just move this up 1, but it's locked in at 0 at all the support other, at points A, C, and D. So now when it's bending, it'll look something like this. Like this deflection moves it up. And then on span CD, it actually dips below. So as I shift this up, right, because this is a continuous structure, it's going to then drop below. And so you could see, like, actually when a truck is on span CD, that's going to reduce my value for the reaction at point B. So I would want to concentrate all my loading on points A, spans A, B, and BC to maximize the value of the reaction at point B. Similarly, I can look at the influence line for dy, and so I'm going to release point D. I'll draw it up 1. You have to imagine the structural shape. Again, keep it constant through. I did my best here to make it continuous so that you can see the shape. So you can see that, to get a maximum value at point D, you could put loads on span AB, and you can put loads on span CD. And then you would want to avoid putting loads on span BC because that's actually going to reduce the value of the reaction at D. Finally, let's draw in a point F, or point E, I'm sorry, in the middle of the beam. And we'll look at the influence line for the moment at E. So just as we did before, we're going to split the beam. We're going to put a hinge in here at point E. And so I'll draw in all my support reactions. I put in my hinge. I put in my positive unit rotation. And again, now because it's symmetric, in fact, the rotation on the left and the right, the rotation is actually going to be equal since it's perfectly in the middle. So it would be like 0.5 on either side. But again, because it's it's an indeterminate structure, we'll have to accommodate for this bending. So if we were to do this in a structural analysis software, we'd have to split it with this hinge, and then we'd have to apply like a unit, moment rotation to get the magnitudes for the rest of the span. But you can see here that the moment at point E is maximized whenever we put loads on span BC. And we would want to avoid loads on the 2 outer spans because that would actually reduce the moment at point E.
Well, it's been a lot of fun going over influence lines with you. I'm excited to talk more about influence lines. We'll probably work more if you end up taking a subsequent bridge design class with myself. We'll definitely get into influence lines, and these videos will hopefully serve as a good refresher. You can always come back to them and remind yourself what we did for influence lines and what do they mean and what their values are. And then also perhaps in structural analysis too, we might do a little bit more with influence lines. So maybe this is a good tool for you to come back and check out. Otherwise, if you're not going out into the world and designing bridges, influence lines might have limited use. So hopefully you understood most of the ideas of this structure. Remember, equilibrium always works. You can always just move the load around. For the purposes of this class, our influence lines are going to be determinate, and then you'll be able to plot them. And even if you struggled a little bit with this, I want you to make sure you understand the concepts of what the influence lines are. So a lot of structural analysis software out there, especially advanced structural analysis software that you would use in a commercial setting, they actually have the ability to plot these influence lines for you and to run moving loads across the structure for you. So you can have the moving load move across the structure, and it'll tell you what the response is at a particular point. So what I want you to take away is, some of what we did on that last page, where, where do I have to put the loads to maximize an effect, right? So where do I put, like, if I had like a moving distributed load, maybe my bridge was going to be loaded with people. What would be the worst case scenario? It would be, when we put the distributed loads on just the spans that cause like the maximum effect, or even the minimum effect at a particular point. When we're talking about moment, right? A max moment or a max negative moment would also be a load case to consider. All right, I think that's enough. I'm looking forward to seeing y'all again. Hope you enjoyed influence lines, and we'll see you soon.